Hello friends, welcome to this lecture on computer-aided power system analysis. We have been looking into the aspect of transformer modeling. In the last lecture, we have looked into the modeling of YG transformer of corresponding to two different vector groups. Today, we would be looking into the aspect of modeling an YGY transformer. So, therefore, today what we are going to do is modeling of YGY transformer. So, it is YGY transformer. So, let us see YGY0 transformer. So, that means it is basically star grounded star transformer, and there is no phase difference between the phase A voltage of the primary side and the phase A voltage of the secondary side. So, then therefore, we again draw. So, we have got, as we have done, so we have got 3 winding. As we have done in the earlier case, we are doing exactly the same case. So, we have got A1, A2, B1, C1, C2, then small a1, small a2, small b1, small b2, small c1, small c2, and the dots are here, 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 here and here. So, as usual, this is star grounded. So, this is phase A, this is phase B, this is phase C, and because this vector diagram would be the same. So, we have already seen. So, then obviously, we also have to star ground them, but only difference is that they will not be grounded. So, we are creating a star connection, but they will not be grounded. So, this is phase A, this is phase B, this is phase small c. So, the voltage, let us say we denote that it is V A now, and V B and V capital C. Now, it is V small c, it is V small b, it is small a. To distinguish between the primary side and secondary side, we can possibly write VAP, VBP, VCP, and let us say this is VAS, VBS, VCS. Otherwise, sometimes this capital C and small c, they are not very much recognizable with each other. So, the current is IA, IB and IC, etc. So, now we draw the vector diagram. Vector diagram you already know. So, this is grounded, this is A1, A2, this is B1, this is B2, capital C1, capital C2, and at the secondary side also we have got the same. So, this is A1, A2, B1, B2, small c1, small c2. only difference is that this point is not grounded. So, now the point is that how do we calculate the current. Now, in the earlier case when this was grounded and when this was grounded. So, then we could only say that essentially the voltage across this particular winding is VAP only, but here in this case the voltage across this winding is not equal to VAS, it is actually VA1 minus VA2. So, then therefore, if I say that this point is neutral, so then therefore, if I say that this point is neutral, so it is actually VA1 minus Vn. Similarly, the voltage across this is VB1 minus Vn, and then similarly the voltage across this winding is actually Vc1 minus Vn. But here we do not know what is the capital N, we just do not know what is capital N. So, then therefore, what we can do is, so then therefore, we really cannot write that IA is equal to Vcp minus Vcs by Z and etcetera etcetera. So, to get around this problem, what we do is, so to get around with this problem, what we do is, we take some circulating current like this, let us say I1, and we take some circulating current like this, say I2 at the secondary side, that is at the Y side. And we also say that Z is the transformer, small z is the transformer impedance. So, then therefore, we can say Y is equal to 1 by Z is transformer admittance. Now, what we will do is, so let us denote this potential. So, these potentials are VAS, VBS, VCS, and this is say VAP, VBP, V capital CP. Now, we would like to write down the KVL across this loop. So, then if we consider this loop, so then what will happen? Now, in this loop, if I start from this point and if I go to this point, what are the quantities, electrical quantities we will get? Now, when I go in this direction, so then we get the equation VAS, so this voltage minus the drop due to this current I1, so Z into I1, and there also would be a drop. Now, because these two windings are because these two windings are actually magnetically coupled with each other. So, then therefore, when we will be traveling in this direction, we will also get one reflected voltage here. So, then therefore, that reflected voltage will also be from this to this. So, then therefore, this reflected voltage would be VAP. Here we are assuming that this is 1:1 transformer. So, VAP. So, VAS minus this drop and then the voltage drop due to this reflected voltage of the primary side to the secondary side. Then we are moving in this direction, and in this direction what is the amount of current? In this direction the current is I1 minus I2. So, it is minus, so then the drop is Z I1 minus I2, Z minus I1 minus I2, then minus the drop in this direction due to the voltage corresponding to this branch. Now, here when we are moving in this direction, so then therefore, we are here encountering the C phase. So, then therefore, here also we will be encountering the C phase, but then this potential VCP is actually from is actually from this to this. So, then therefore, when would be moving from this side to this side here, it would be actually rise. So, then it would be VCP, right. So, it would be VCP and then minus VCS is equal to 0. I repeat. So, then therefore, we start. So, as if at this point, as if that there is a rise in voltage Vs minus the drop, this is nothing but the impedance drop due to the flow of current I1 in this branch, that is ZI1. Then there would be another drop due to this reflected voltage of phase A. See, this is phase A and this is phase A. Then there is another drop, because in this direction current is net current is I1 minus I2. So, then therefore, there is a drop Z into I1 minus I2. Now the reflected voltage of the primary side of phase C is actually from this side to this side. So, then therefore, when we are moving from this side to this side, to this side, it would be nothing but a rise in voltage. So, then we will get VCP and then of course, then it will be the drop VCS. So, this is the equation. So, this equation is actually, we should actually write that KVL in loop A1 C1. So, we are writing KVL in loop A1 C1. So, then therefore, we can write down the equation. So, then therefore, we can write down the equation as, so from this we can write down that ZI1 plus ZI1 minus ZI2. So, ZI1 plus Z into I1 minus I2 is equal to VAS minus VAP is equal to VAS minus VAP, VAS minus VAP plus VCP minus VCS plus VCP minus VCS, or in other words, it is 2ZI1 minus ZI2 is equal to VAS minus VAP plus VCP minus VCS. So, this is equation number 1. Now, we consider another loop. Now, we consider the loop C1 B1. So, now we write the KVL equation in the loop C1 B1. So, we write KVL in the loop C1 B1. So, when I write down the KVL in the loop C1 B1, so we start from this point and we reach at this point. So, when we start at this point, so my voltage is VCS. So, my voltage is, first voltage is VCS. Then the current in this direction is I2 minus I1. So, then the drop due to the current in this direction is ZI2 minus I1. So, then the drop is Z into I2 minus I1. Then there would be a drop due to the reflected voltage of phase C here. So, then this reflected voltage is also from this point to this point. Essentially the instantaneous polarity of this reflected voltage would also be from this point to this point. So, it would be minus VCP. So, it is minus VCP. Then the drop in this direction is, in this branch the current is only I2. So, then the drop is minus ZI2. So, minus ZI2. Then now we should also have, now here in this branch the reflected voltage is VBP, but again this VBP is actually rising from this point to this point. So, then therefore, therefore, the reflected voltage here at this branch will also be rising from this point to this point. So, then therefore, this is a rise in voltage. So, then therefore, it should be plus VBP and then minus we reach this voltage VBS minus VBS is equal to 0, right. So, it is minus VBS is equal to 0. So, then therefore, we write Z I2 minus I1 plus Z I2 is equal to VCS minus VCP plus VBP minus VBS. VCS minus VPP plus VPP minus VBS. So, then therefore, minus ZI1 plus 2 ZI2 is equal to VCS minus VCP plus VPP minus VBS is equal to. So, this is the second equation. So, now what happens? We have got. So, now therefore, what we have done so far, we have because at the secondary side I do not know this voltage of this point N. So, basically this point is N or B2 the same. So, we have created two loop current I1 and I2, and by writing KVL equations in two loops we got two loop equations. These loop equations are given by 1 and 2. So, now we need to solve these two equations and find out the expression of I1 and I2. So, to do this, so what we do is we do multiplication of 2 by 2. So, now is actually minus 4 I1 plus it is minus 2 Z I1 plus 4 Z I2 is equal to 2 into VCS minus VCP plus VBP minus VBS. So, this is equation 3. Now, we do 1 plus 3. If we do 1 plus 3, so then what happens? This cancel out and this becomes 3 ZI2 is actually VAS minus VAP plus VCP minus VCS plus 2 VCS minus 2 VCP plus 2 VBP minus 2 VBS, or in other words 3 ZI2 would be, now take all these things common. So, what we get? VAS minus 2 VBS. So, first minus VAP plus 2 VBP, and so it is, I have got minus VAP plus 2 VBP minus VAP plus 2 VP minus VCP minus VCP plus VAS then minus 2 VBS minus 2 VBS minus plus VCS. So again let's cross check. So let's cross check. So cross check is VAP plus 2 VPP minus VCP plus VAS, then minus 2 VBS and plus VCS. So then therefore I2 is equal to, so then therefore I2 is equal to, so then therefore I2 is equal to y by 3 into, what is y by 3? Y by 3 into all the minus VAP plus 2 VBP minus VAP plus 2 VP minus VCP. So we are just writing all of them, plus VAS plus VAS minus 2 VBS plus VCS minus 2 VBS plus VCS. So this is the expression of I2. So let's, so this is the equation 4. So we have got the expression of I2. Now we have to also get the expression of I1. So to get the expression of I2, what we do is we multiply this equation by 2. So by 1 into 2 by 1, equation 1 into 2. So what does it give us? This give us 4z I1 minus 2z I2, 4z I1 minus 2z I2 is equal to 2 into VAS minus VAP, 2 into VAS minus VAP plus VCP minus VCS plus VCP minus VCS. So this is equation say 5. Now what we do is we add 5 and 2. So if I add 5 and 2, so what we get is, if I add 5 and 2, so we do 5 by 5 plus 2 by 5 and 2. So what we get? So 5 and 2 we get is 4z, 3z I1, 3z I1 is equal to VCS minus VCP, VCS minus VCP plus VBP minus VBS plus VBP minus VBS plus 2 VAS minus 2 VAP plus 2 VCP minus 2 VCS. So then therefore what we get is 3z I1, we collect everything. First we collect VAP, so when we collect VAP, so we get minus 2 VAP, there is only VAP minus 2 VAP, so minus 2 VAP, so minus 2 VAP plus VBP, so minus 2 VAP plus VBP, and then plus VCP plus VCP, and then what we get is plus 2 VAS plus 2 VAS plus 2 VAS, and then what we get is there will be minus VBS and minus VCS. Again let us cross check. So let us cross check again. So cross check is minus 2 VAP that we have got, plus VBP that we have got, plus VCP, this and this they give me plus VCP, 2 VAS. So, this gives me 2 VAS minus VBS, this gives me VBS, and only these two are remaining, everything else has been taken care of. So, this two give me minus VCS. So, then therefore, I1 is equal to I by 3 minus 2 VAP Six and 4 are the equations of I1 and I2. So, with these equations of I1 and I2, now we are ready to write down the equation. Now, from here what I can do? Now, IA1 or rather I small a, or now let us say that these currents are denoted as, now let us say that these currents are denoted as let us say IAS, this current is ICS and this current is IVS, this current is I ICS. So, this current is IBS, this current is ICS, this current is IAS. So, then therefore, what we can do, right, IAS is equal to I1. So, now from this equation I can write down that, now we can write down now IAS is equal to I1, IBS is equal to minus I2 and ICS is equal to I2 minus I1, I2 minus I1, so I2 minus I1. So, then therefore, IAS is equal to I1 is this, IBS is equal to minus I2. So, then IAS is equal to, so then therefore, IAS is equal to I1. So, IBS is actually is equal to minus I2, IBS is equal to minus I2. So, then therefore, y by 3 is minus I2 VAP minus 2 VBP plus VCP minus VAS plus 2 VBS minus VCS. So, this is equation 7, and ICS is equal to I2 minus I1. So, ICS is equal to, and ICS is equal to I2 minus I1. So, it is y by 3 minus VAP plus 2 VPP. So, it is minus VAP plus 2 VPP minus VCP, I2 plus VAS minus 2 VAS plus VAS minus 2 VBS plus VCS. So, this is I2 minus I1. So, it is plus 2 VAP plus 2VAP minus VPP minus VCP minus VPP minus VCP and minus 2VAS minus 2VAS plus VBS plus VCS plus VCS. So then therefore ICS is equal to Y by 3 into, let's see, VAP plus VBP minus 2 VCP, then minus VAS minus VBS plus 2 VCS. So this is equation 8. So now what we have got? We have got the 3 equations at the secondary side. Now we have to get the 3 equations at the primary side, and then we have to write down the inter Y bus matrix, right. So this we will do in the next lecture. Thank you.